I'm going to present no Linux, no problem, fast and correct Windows binary fuzzing via target-embedded snapshotting. So fuzzing is a method for automated software testing. And in a nutshell, the idea is we're going to try to break the program we're testing by throwing a bunch of randomized inputs at it. So here's a real world example. Here's some JPEGs that were generated by a fuzzer. So for testing this parsed JPEG, we're going to throw those at it, try to find one that actually crashes the program. So let's see what that looks like as an algorithm. So step one here, we're going to generate a test case. Step two, we're going to actually execute the program we're testing and have it parse that test case. Then finally in step three, we're going to observe the result of doing that. So this is where we're going to check and see if the program actually broke. Because if it broke, then we found a bug, which we can then fix. But the point I want to make here is the faster we can run this loop, the more inputs we can test. And the more inputs we can test, the better chance we have of actually finding a bug. So generally speaking, fuzzing depends on speed. Faster fuzzing is more effective fuzzing. And typically, the execution step is the limiting factor in this loop. So on Linux, execution is very fast out of the box. Primarily just due to the availability of the fork system call, and that translates to fuzzing being effective. On Windows, we don't really have an equivalent to that, which leads to a situation where, despite the fact that Windows has this really big software ecosystem, fuzzing on Windows is actually a lot less effective than on Linux. So our challenge for this project is, without kernel support, like what Linux has, how can we build an efficient Windows fuzzer? And here's one solution to that. So this is persistent mode. This is the basis of an existing Windows fuzzer. So we're going to start off creating the process like normal. We're going to load it and let it initialize. And then after we execute the body of the code, which is the code that we're actually trying to test here, we're actually going to hijack the control flow of this program to jump back to the beginning of that code that we're testing. So this way we skip the process initialization and teardown, and we can just execute the body over and over again. So this is fast, but it's not correct because, as you may anticipate, executing the body can, of course, change the state of the program, or the state of the process. And then the next time you try to run this code that you're testing, the state of the process could be different. And so out of the box, many binaries will actually crash with persistent mode. So that brings us to our approach in a nutshell, which is adding these two steps to persistent mode. So we load the target binary into new process. We let it initialize as normal. Once it's initialized, though, it's in the state that we want it to be in every time we run the body or the code that we're testing. So at that point, instead of immediately proceeding to the body and possibly changing that, we want to keep that, so we're going to save the state first. Then we execute the body, we can change it to whatever. When we return from the body and go to execute it again, first we're going to reset the state. So that way each execution of the body should start with the correct state. So this way we can be fast like persistent mode, but we can still be correct. So now I'll talk about our implementation of this technique. So we based our implementation on WINI, which is an existing Windows fuzzer. And I'm going to go over 5 of the main steps that happen during fuzzing. So first, we inject the DLL that has our code. Then the DLL main function will run, which sets up our hooks and interposition on the target process. Then the target will initialize, which we already saw in the previous slides. We'll take the state snapshot. And then finally, once we have that, we're ready to proceed to the main fuzzing loop, which is just running the code that we're testing and restoring the state over and over again. So here's that in a diagram. So we start with the target binary we're testing and our DLL. We inject that into a new process, run our DLL main function, which sets up our interposition on the target so that once it initializes and puts itself into the state we want it to be in, we first go to our snapshot function, which will save the state of the process at that point, and then proceed to the body of the code. And now we're ready to start that main fuzzing loop where we run the body, restore the state of the process, and keep doing that over and over again. And then after some large number of iterations, we're going to actually exit the process completely and start this diagram all over again. This is basically just a catch-all for any random elements of state we may have missed with our target-embedded snapshotting system. Persistent mode also does this, but the overhead of doing this is negligible if we do it like once every several million iterations or something. So now I'll talk about the elements of program state we keep track of and how we restore them. So there's the stack, registers, heap, and global variables. So for the stack, we save the base pointer and stack pointer before the target runs. And then when it runs, because of the way the stack works, everything it adds, in other words, everything we want to get rid of after it's done running, is going to be above the old value of the stack pointer. So we can rewind those pointers and clean up everything the target just added to the stack. For registers, we would consider that there are generally two types. Simple values where the meaning is contained in the value of the register itself, and then pointers where the meaning is contained in some other information somewhere else. But we reset all registers to their original value because we avoid ever actually returning from the target function and running any code after it that would clean up any parameters that are passed into it. So first, before the target runs, we copy all those register values. The target runs, it's going to change a bunch of those registers, and then finally we can restore them from the snapshot. So resetting the heap for us is all about preventing memory leaks, essentially, because we're fuzzing this program, so we're actually trying to break it. So we have to anticipate that it might exhibit some incorrect behavior. And in our case, we're running this program over and over again in the same process, so we're actually circumventing the normal operating system level cleanup that would happen automatically. So even a small memory leak, say like 1 page every iteration, could be enough to actually cause the system to run out of memory eventually. So what we do is we use function hooks on all the API calls that allocate heap memory, so we can keep track of those and prevent memory leaks. So before the target runs, it hasn't allocated anything onto the heap. We have nothing in our list. It runs, and every time it allocates something, our function hooks are going to keep track of those pointers and then remove them if they get freed, such that by the time we finish running the target, everything that's in our list is a memory leak, so we can just get rid of it safely. So global variables are all stored in a special section of memory in the process, and we keep track of all of the global sections that are writable. And we use guard pages and a guard page handler to actually track which of those global variable pages were modified during runtime, just as an optimization so we can avoid restoring the ones that were not modified. So before the target runs, we create a complete copy of all the writable global pages. The target runs, and anytime it changes a page in there, we're going to get a guard page exception, and we're going to mark that page as modified, so that when we go to clean up the state of the process, we can actually only restore those pages that were actually modified. So now I'll talk about our evaluation. So I'll talk about correctness, performance, and bug discovering ability. So we compared to Winnie and WinAFL. We used Azure instances on Windows 10. And we made sure to run enough trials to make sure the results were statistically significant. Here's our benchmark corpus, so you can see we have a mix of proprietary and open source, different file formats, different sizes. So first I'll talk about the correctness test. So we implemented this as a new fuzzer mode that checks for state corruption that we missed with our state restoration mechanism by comparing program states. So here's how it works. So we have this large collection of inputs we're going to use to test the state restoration mechanism, and we're going to pick one of them. We're going to parse that in a new process first, and then save the state of the process immediately after parsing that input. Then we're going to parse a bunch of the other inputs, all of the other inputs that we have, and then finally that same first input again. So if in fact we did miss cleaning up some element of state somewhere while we were parsing one of these inputs, we would expect the state of the process to have changed between the first and the last run that we did. So then we just compare these two snapshots. Here's our results for throughput. So you can see we had a significant performance improvement versus both WINI and WinAFL. And if one of the benchmarks is excluded here, that's just because it didn't run with that fuzzer. Here's our results for code coverage. The Man-Whitney U-test we did showed that 2 of these were not necessarily statistically significant differences, so they're marked with an asterisk here. But overall, we had a plus 15% improvement versus WINI and plus 5% versus WinAFL. Here's our bug discovery time comparison. So for this, we compared the average time each fuzzer took to find specific bugs. And some of the benchmarks we used for this used older versions. So this is kind of like a known bug time comparison. So there were 10 of those in total. WinFuzz found 8 of them. And WINI and WinAFL found 3. So you can see the results here. Plus 56% speed up versus WINI on average, and 23 times versus WinAFL. And then finally, just to demonstrate the capability of WinFuzz to find actual real-world undiscovered bugs, we also ran some additional experiments just with WinFuzz with some new benchmarks, specifically for the purpose of finding zero-day bugs in programs. So you can see we found 9 of those total, and we reported all of these to their authors. Yeah, now I can take any questions.